Section 6.2, Volumes. Let S be a solid that lies between x equals a and x equals b. If the cross-sectional area of S in the plane px through x and perpendicular to the x-axis is a of x, where a is a continuous function, then the volume of S is the limit of the sum of a of xi star delta x, which we know is a Riemann sum, so that is our integral a of x from a to b. So what we're basically saying is you take some particular point x, you draw a plane that cuts through, so you slice through your three-dimensional object at that plane. You end up with this cross section. You do that at sample points xi star, and then you approximate the volume of the solid using these cross-sectional areas expanded over an entire interval. So when you fatten out each cross-section, you get a volume, and then you stack up these volumes and you get an approximation for the volume. When you stack up enough volumes, in other words, you take the limit, then you get the exact volume. So in this case, we have about 7 cross-sectional volume pieces over here. And as we take the limit, these pieces become thinner and thinner because the intervals get smaller and smaller, and we get the actual volume. So this is pretty much the same as we were doing before, except that now sample points are used to determine an area instead of determining a y value or a height. So we just stack up all these little areas. It's kind of like when you have a piece of paper. It has some sort of area. If you stack up enough of those pieces of paper, then you get a volume of a rectangular solid instead of just a two-dimensional area. Let's do an example by showing that the volume of a sphere of radius r is 4/3 pi r cubed. So first we should try drawing our sphere, and let's see, put our axes, so that could be x, this could be y, and we want to show that this thing is three-dimensional, so maybe I'll draw a little thing inside. And then our axes cut through. Okay, so then r is over here, because this is a sphere of radius r. We want to look at a single cross-section. So if we were to slice this perpendicular to the x-axis, then we should get a circle. So the circle has, well, if the radius of this thing is r, that means that this is r. So the circle has a radius that's equal to the height, which is the y value. If you go along over here, from left to right, we're looking at a particular x value. Looks like we get a nice triangle like that. So we can write the area as a function of x if we can eliminate the y value, because then we can just write the area of this circle as pi r squared. Without the y, it would just be pi times some function of x squared. So let's see what y is. Well, x squared plus y squared is r squared, because it's a triangle by Pythagorean theorem. So y is the square root of r squared minus x squared. So that means that our area function of x, which is the area of this circle, is pi times y squared, which we can now replace with pi times r squared minus x squared. Notice we didn't want to leave it as pi y squared because we needed a function of x, because we're stacking up all of these arbitrary circles along the x-axis. So each one becomes a disk when we're stacking it up with a tiny little change in x, delta x. So now we can get the volume. Our volume will be the integral from minus r to r of a of x dx. Well, that's the integral from minus r to r of pi times r squared minus x squared dx, which is 2 pi, because that's a constant, we can take it out, times the integral from 0 to r of r squared minus x squared dx. Notice we're using the fact that the sphere is symmetrical, so instead of going all the way from left to right, I can just take half of it and double it. So I changed my, not going from minus r anymore, I'm just going from 0 and doubling it. So then this equals 2 pi times r squared x minus x cubed over 3 from 0 to r, which is 2 pi times r cubed minus r cubed over 3, which is just 4/3 pi r cubed. Okay, so we proved it. Each time we do this, we're going to be looking at some sort of disk, and then we find the area of the face of the disk, and then, well, that's the area of a circle, so it's just pi r squared, so we have to figure out what that radius is every single time, and then make sure that we write it as a function of x, and then do our integral. Let's find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals square root of x from 0 to 1. And we'll illustrate the definition of volume by sketching a typical approximating cylinder. So we've got this graph. Here's y, here's x, here's y equals square root x, and we're cutting it off at 1. Let's see, we've got we have to rotate this about the x-axis, so that means we're rotating over here. So when we do that, it becomes something like this. How about I draw the rotation first? So here's y equals square root of x, and then it revolves around and around and around, and it ends up becoming this three-dimensional solid. So now, here's 1, here's the x-axis sticking out, and here's my y-axis still. We want to try to drawing a typical approximating cylinder. So we start with our picture in the plane, and we draw a rectangle. So if this is at x, then the height of the rectangle is square root of x. Then the rectangle spins around and around the x-axis, and it becomes a cylinder. Something like that. The cylinder has a thickness of delta x and some area, a of x, which is the function. So the cylinder is a little disk. The area of the face of the disk is the area of a circle, so it's pi r squared. Notice in this case, the radius is still the y value, so that's still square root of x. That's how high this goes. So this is going to be pi times square root of x squared, which is just pi x. So that means that the entire volume of one arbitrary disk is a of x times delta x times the thickness. So that's pi pi x delta x. So that's what we're going to integrate. So we take the integral from 0 to 1 of a of x dx, which is the integral from 0 to 1 of pi x dx. And that's just pi times x squared over 2 from 0 to 1, which is pi over 2. Let's find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0, about the y-axis. So we'll draw something like this. So it looks like we're going from x equals 0 to y equals 8, so we don't have to worry about the negative part so much. So we'll just draw a little bit of that. So that's y equals x cubed. And we need y equals 8. So if this is the y-axis, then this is y equals 8. And here's the line x equals 0. Here's 0, the x-axis. So I think that's pretty much everything we need. Now we have to rotate. So we need to go around the y-axis this time. So I'm going to do a little better arrow. So I'm rotating around the y-axis, spinning around and around and around, and I end up with a solid because it starts spinning like this, spins around, do a little bit bigger, something like that. So this part is this part, and then it spins and completes the entire three-dimensional solid. So here's my y-axis coming out at y equals 8. So I drew it a little bit smaller. This was a little bit bigger than this, but you get the idea, I think. Let's take a look at approximating cylinder. I really should use another color for that. So how about we do, let's see what this looks like. So if I look at a single rectangle over here, let's see what it looks like over here. Well, notice I'm not choosing a rectangle vertically, because if I do that, then I have to get the area underneath y equals 8, and I have to cut out this area over here. So I would have to subtract two different functions. Whereas if I just do this rectangle, I can just think about the area below this curve right over here, y equals x cubed. So that means that this thing is the height, which is the how far it goes in the x direction. So let's rewrite this in terms of x. This thing is x equals cube root of y. So that means that this guy has a width of cube root of y, because the width of this rectangle is the x value. When I draw this cylinder in my three-dimensional shape, it looks something like this. It goes at that whatever y value I picked. The radius is this thing. So this is the radius. It's going to be the x value, which we said is cube root of y. And then this thing is three-dimensional still, so it has a tiny little thickness, delta y. Because we're stacking these up vertically about the y-axis, each thickness for each of these little discs, each of these little cylinders, is a tiny change in y. So our integral, it looks like, would be way easier if we do it in terms of y. So instead of doing area as a function of x, I'll write area as a function of y. In this case, how far we go out is the x value. So the radius of the disk is x. That's this right over here. So that's pi times x squared, pi r squared. However, we need this as a function of y now because we're stacking up vertically. If we're stacking up vertically to fill up our solid, we cannot write it as a function of x. Just like if we were stacking up horizontally, we couldn't write it as a function of y. So this will be pi times cube root of y squared, which is just pi times y to the 2/3. So now let's look at the volume of a particular disk, or an arbitrary disk. It'll be a of y times delta y. Well, now that's going to be pi times y to the 2/3 delta y. So we can compute our volume as the integral from 0 to 8 of a of y dy. And that's the integral from 0 to 8 of pi times y to the 2/3 dy. So we integrate by reverse power rule. We get 3/5 y to the 5/3 from 0 to 8, which is just 96 pi over 5. The region R enclosed by the curves y equals x and y equals x squared is rotated about the x-axis. Let's find the volume of the resulting solid. So we've got our x and y axes. We've got the curve y equals x and the curve y equals x squared. How about I draw y equals x squared first? And then I'll switch to another color, and we'll get y equals x. Okay. It looks like this is our region R that we want to get the area of in order to rotate and get the volume of. So we should see where these guys intersect. Well, pretty clear from over there it'll be 0, 0. When x is 0, y is 0 for both of these. And if we plug in 1, 1, we can see that that's another intersection point. Or you can actually solve the system of equations. So we want to take this and rotate it about the x-axis. If we do that, then we get a solid. So it looks like if I rotate this around the x-axis, this will be on the outside, the green one. So let's draw that. And then the blue part, actually, how about I show you the way that this thing's rotating. So I'll draw that. And then it rotates around. And on the inside is the blue part. So you're not going to be able to see that from the outside. It's inside the solid. The solid is 3-dimensional. So it looks something like this. So it's like this 3-dimensional cone kind of shape. However, notice that there's a big gap over here. So there's a big gap inside. So the cone is hollow on the inside. It's just got this little thickness over here. But otherwise the inside is hollow. So if I look at a particular rectangle, like that, then it corresponds. Oh, yeah, I forgot. Let's do another color. Look at a nice little rectangle. It corresponds to some, like this little piece over here, which will be, well, that's actually not such a good illustration. So the rectangle is over here. That's like over here. However, there is this gap over here, which is like the inner part when it rotates around. So you could see that this thing becomes basically a disc with a hole through it when you rotate it around. So that's really what I should be drawing. So I'll draw a nice little disc with a hole in it. We usually call those washers. The disc has a little thickness, so I'll draw a little thickness, and that thickness is delta x. Okay, so now we really need to get the area of the face of this washer in order to do our integral. So how about we try drawing that? If this is the washer, then this is the inner part. We've got some radius over here, little r, of the smaller part of the washer, the hole. And we've got a radius, let's say big R, of the outer part. So let's say this is a big R. So we want to find this area of the washer. Well, that area, I might need the space later, so how about I do it over here? That area is just all of this over here. So that's if I take the outer circle and I cut out the inner circle. So that's pi times big R squared minus pi times little r squared. So that means that the area of the washer that I'm going to integrate over, pi times big R squared minus pi times little r squared. Looks like this height is this radius, so that's this r. So that's just x squared. So little r is x squared. And then big R is this height, which is over here, So that's x, because that's the height of the green function. So this becomes pi times x squared minus pi times x squared squared. We plug in each of the radii. One of them was x, one of them was x squared, and then we do not forget to square them afterward. So this ends up becoming pi times x squared minus x to the fourth. So our volume is the integral from 0 to 1 of a of x dx. And that's just the volume. Sorry, the integral from 0 to 1 of pi times x squared minus x to the fourth dx, which is pi times x cubed over 3 minus x to the fifth over 5, and that's 2 pi over 15. So the hard part for each of these problems is drawing everything that's going on, figuring out the area of a typical disc or washer depending on the problem, because sometimes there's a hole in the middle of the thing that you're trying to integrate over, the thing that you're trying to sum up. Let's try finding the volume of the solid obtained by rotating the region in the previous example about the line y equals 2 instead. So we're going to take this thing, and instead of rotating it around the x-axis, we're going to draw the line y equals 2 up here somewhere, and then we're going to flip it around over there. So when we do that, we're going to get something like this. We get this kind of, let's see if I can draw this. Now the y equals x squared curve is on the outside, and the other one is on the inside. So let's try drawing that green curve still. So this is the flat green curve, the line y equals x. Because if we rotate it around this line over here, then when it flips around, the green part is on the inside and the blue part is on the outside. So how about I label this? Put that over here. And I need some axes. So this is the line y equals 2 that I rotated around. So it cuts through the inside of this object. And here's my y-axis. Here's x equals 1. And this part on the outside is y equals x squared. So let's try drawing a an arbitrary little disk. Not so easy to draw these things. But I'll attempt it just because I really want you to attempt it. Yours definitely can't be as bad as mine. Okay, so that's the inner radius. And here's the outer one. And then it has a little thickness. Okay, something like that. So this is at a particular x value. Let's try drawing just the disk by itself. So really probably should have just copy and pasted it. Oh well. Yeah, you could tell I didn't pay close enough attention in art class. If I look at this disk, it's floating above the x-axis. Right, there's a little thickness over there, a little part where it's floating. So the height over there is the height of this function over here, which is x squared. So this little part is x squared. So if from here to here is the line y equals 2, then that means that from here to here is 2, from here to here is x squared. So this missing piece, which is the big radius, must be 2 minus x squared. Let's see if we can get the smaller radius now. Well, that'll be from here to here. So if from here to here is 2, I just need to know how much to cut out. Well, from here to here is the distance from here to here, which is the y value over there for this function. So that's just x. So little r is 2 minus x. So I think we now have enough information that we can do our integral. The area, which is pi times big R squared, minus pi times little r squared for our face of our washer, is pi times 2 minus x squared for big R, and then we square it, minus pi times little r, which is just 2 minus x without the square, but then we square it because it's the radius. So our volume is the integral from 0 to 1 of a of x dx, which is pi times the integral from 0 to 1 of 2 minus x squared squared minus 2 minus x squared dx, which is pi times the integral of x to the fourth minus 5x squared plus 4x after you expand and simplify a little bit. So that ends up becoming pi times the antiderivative x to the fifth over 5 minus 5 times x cubed over 3 plus 4 times x squared over 2, all evaluated from 0 to 1, and that's just 8 pi over 15 when you do the math. Let's take the same solid we had before and now rotate it about the line x equals minus 1. So we start with our y-axis. I'll draw, let's use green. This is the line y equals x. And then our blue part is still the parabola y equals x squared. So then it gets rotated around, but it gets rotated around the line x equals minus 1, so we're going to need quite a bit of space over here. Because x equals minus 1 could be over here. Let's say. If this is 1, then yeah, that's roughly minus 1. So here's x equals minus 1. And I want to rotate around this thing. So my green part gets flipped in the opposite direction, gets rotated around, and my blue part does too. So you can't really see the solid. I'm not going to draw it all the way around, but it rotates all the way around, something like that. Instead, what I'll do is I'll just draw one of these discs because I think that'll be a little more helpful. First, we should probably finish labeling, but before I even do, notice if I stack up a disc like this, and then a disc like this, and then a disc like this, I'm stacking the discs up vertically now. So each one is going to have a tiny change in y because it's stacking up along this, not really y-axis, it's around x equals minus 1, so it's the y-axis x equals 0 if you moved it over 1. But in any case, I'm stacking up along y, so each one has a tiny change in y, so I'm going to have dy. So I want everything as a function of y. So instead of writing y equals x squared, for this guy, I'll write x equals square root of y, because it's just in this first quadrant anyway. And then for my other one, I'm not going to write y equals x, I'll write x equals y. So now I'm prepared, I think, to draw a nice little disc. Maybe I'm not prepared, but I'll do it anyway. So we need a nice inner radius, smaller, this is the hole, and then for the outer part, and then there's a little thickness. Sorry, not disc, it's a washer again, because there's a big hole in the middle. Okay, for our washer, let's see if we could figure out what are our big radius and our small radius. So our washer takes place at a particular y value, and we would like to know the smaller radius. Well, from here to, let's see, if I look over here, I know that this distance from here to here is the distance to my green function. So that's just whatever the x value is over there, which is equal to y. So that's this over here. I also know that from here to here is the distance from 0 to x equals minus 1. So this distance is 1. So that means that my total radius for my smaller radius is just 1 plus y as a function of y. So now I need the bigger one. Well, the bigger one, I need to know how far it is from here to here, which is how far it is for this function over here, which is x equals square root y. And then from here to here is 1 again, so that means that the entire big radius will be 1 plus square root y. And that actually, not such a good drawing. I know you're shocked. Okay, a little bit better. So now I think we can write out the area function. The area of y will be pi times the big radius squared minus pi times the small radius squared, which is just pi times 1 plus square root of y squared minus pi times 1 plus y squared. So our volume is the integral of this area function dy, because we're stacking them up vertically. And that'll be pi times the integral from 0 to 1 of 1 plus square root of y squared minus 1 plus y squared dy. So that becomes pi times the integral from 0 to 1 of 2 radical y minus y squared dy, which is equal to pi times 4y to the 3 over 2 over 3 minus y squared over 2 minus y cubed over 3 from 0 to 1, which is pi over 2. So that's the volume of the solid if I had actually drawn it. I only really drew these parts at the end, but you can imagine the rotation behind it. The figure shows a solid with a circular base of radius 1. Parallel cross sections perpendicular to the base are equilateral triangles. Let's find the volume of the solid. So up until now, we found the volume of a disk. We found the area of a face of a disk, so that we could find the volume of the disk and stack it up. Then we found the volume of a washer and stacked that up. Now we're going to find the area of a whole bunch of little triangles and stack those up. So if I roughly draw this solid sitting in the plane, it looks something like this. Where here's the y-axis cutting through it. And here's the x-axis. I feel like my pictures get worse and worse. Something like that. And then I wanted to make this thing look a little bit 3D. So there's the circular base. Okay, I would like to be able to draw some triangles. Well, first, how about we draw the circular base a little bit? good enough. I can move it a little bit. Oh, nice. Okay. So here's 0. And yeah, that's pretty good. Okay. Notice that this part of the base is going to be y equals square root of 1 minus x squared, because the base has a radius of 1. It's a circle, so it's x squared plus y squared equals 1. And if I want to solve for y, I can do that. That'll come in handy very shortly because I'm about to draw these triangles. We're about to try to draw these triangles. So an arbitrary triangle looks something like this. Right. Draw a couple of more of them so you could see. They just slice through as triangles. So how about I draw a nice big-ish one. See if I can do it. Okay, this is happening in a particular x value. And let's name our triangle A, B, C, so you can see what's going on. This part over here is just the base, so that's just the circular bottom. So that means that the only part that we can see in our circular bottom is from A to B, right over here. You just see the line of the triangle at the base. And then here's the x value we're looking at for our particular slice. So here's A and here's B, the vertices of the triangle. So that means that if I want to know what the length of this thing is, that's just this part over here. And remember, I put this flat against the plane. Here's the y-axis. So over here is the y value. So over here is the y value, which is why we calculated it as y equals square root of 1 minus x squared. So that means if I want to draw this triangle, it looks something like this. Here's A, B, C, and it's equilateral, they told us, right? Equilateral triangles. So here's 60 degrees, and here's 60 degrees, and the top's also 60 degrees. That means that the base of the triangle, well, if I cut this in half, this part's y and this part's y. That's this part and this part. Well, that's also convenient because now this is a 30, 60, 90 triangle, just the half of it. So if it's a 30, 60, 90 triangle, remember that the part opposite the 30-degree angle, if it's x, then the height is x rad 3. So this height is rad 3 times y. And then the hypotenuse is 2y, but we don't need that. Well, now we can get the area of this triangle, and we can use that to stack up all these little triangles with tiny little thicknesses, dx, delta x, and we can make our solid. So the area of a triangle is half of base times height, so it's half of 2y, because 2 of these guys, times the height, which is rad 3y. So we said y is equal to square root 1 minus x squared, because x squared plus y squared equals 1 for the base. So that means that this is half times 2 times 1 minus x squared times rad 3 times 1 minus x squared, the square root. So that's rad 3 times 1 minus x squared, because the half and the 2 cancel, and the square roots cancel for the 1 minus x squared. So our volume becomes the integral from minus 1 to 1 of a of x dx. That's just the integral from minus 1 to 1 of rad 3 times 1 minus x squared dx. which is 2 times the integral from 0 to 1 of rad 3 times 1 minus x squared dx. Because, remember, this thing's symmetrical. So I can just go from 0 to 1 instead of going from minus 1 to 1, and I can just double it. It'll save me a little bit of hassle because then I can subtract 0. So this becomes 2 rad 3 times x minus x cubed over 3 from 0 to 1, which is 4 rad 3 over 3. And that's the volume of this guy. Let's find the volume of a pyramid whose base is a square with side L and whose height is h. Actually, I don't want to draw the axis because it's going to be on the inside. So how about I just draw the nice triangular, well, not triangular, but, well, yeah, triangular, I don't know. You can call it square pyramid because the square is the base is a square, but the sides are triangles. Okay. Nope. Alright, a little bit better. And I need a axis now. A little more. Then it cuts through. And this is h. So that means that the square has side length L, so this is L. And I'll draw the inside too. Okay, here's the y-axis, here's the x-axis. Go a little bit farther, 0. And let's take a look at a slice of this in the plane. So if I want to look at this nice and flat to get a better idea of what's going on, then it's just this nice big triangle. Okay, that's supposed to be symmetrical, so just imagine this is still L, and from here to here is the height h. Okay, let's try drawing one of these little squares we're going to stack up. Because notice, if we tried doing the volume of this, we're just stacking up this little base square over and over and over and over and over and over. So stacking up all those squares is going to give us the volume. So let's look at one at a particular arbitrary x value. So that, not so easy to draw these things. Let's see. No, it's going to cut off my x. Go closer. See how far. Okay. Yeah, so that's roughly a square slice. So if I look over here, that square slice slices like that. So if one side of the square has length s, then this is s. And then that means that from here to here is the x value that I chose. Could be anywhere. So that's from here to here. So I think we have enough information now that we could figure out what the area is. Notice that this triangle over here and this smaller triangle over here are similar triangles. So I can take x divided by this base, which is h, and that must be equal to this part of this triangle divided by this part of this triangle. So that's half of s, or s over 2, over L over 2. But I can multiply top and bottom by 2 and just see that that's going to be equal to s over L. So that means I can cross multiply L times X divided by H, and that'll be what S is equal to. So the side length of the square is L times X over H. So that means that the area of a square, which is S times S squared, is L squared over H squared times X squared, which is perfect because if this thing has side L and height H, those are constants. So the only variable left is X. So now I have everything in terms of X. So I can do our volume as the integral from 0 to whatever the height H is, some constant, of a of x dx. And that'll be equal to the integral from 0 to h of L squared over H squared X squared dx. These guys are constants, so I can pull them out. That's just L squared over H squared times X cubed over 3 from 0 to h. And that's just L squared H over 3. Now, you might be thinking, okay, how did you know to put it against the x-axis like that? And you don't know right off the bat. You could have drawn it vertically also, and then done the entire integral, and you would have gotten the exact same answer, but it actually gives you a much more complicated integral if you do it like that. So sometimes you might want to put it in different positions in the plane so that when you're stacking it up and then you're doing your integral, you get the simplest one possible. Notice when we lay it against the x-axis also, we can do everything as a function of x, which is also kind of easy sometimes if we don't like messing around with y. Okay, say a wedge is cut out of a circular cylinder of radius 4 by 2 planes. One plane is perpendicular to the axis of the cylinder, the other intersects the first at an angle of 30 degrees along the diameter of the cylinder. Let's find the volume of the wedge. So here's my cylinder. Now let's try actually drawing this as big as possible so we can see what's going on here. Okay. Yikes. Alright, getting a little bit better. Not much, but a little bit. Alright, that's my cylinder. Let's put it along our axes. So how about this can be the x-axis, and this can be the y-axis. We need to cut a wedge out of this thing. So we can cut a nice wedge out. Not so easy to do. Something like this maybe. Okay, so that's like a wedge cut out at the bottom. Okay. Notice that the base is a circle of a cylinder, and it's a circle of radius 4, so that's x squared plus y squared equals 4 squared. So if I want to know the y value over here, the y value is the square root of 16 minus x squared. Let's try drawing one of these slices. Notice if I slice straight down through the wedge, then I'm slicing through, and I'm going to end up with one of these pieces, which is a triangle. So let's try drawing that triangle that we're going to stack up. This is always the Herculean task. Alright, whatever, fine. So it's a nice little triangle. Let's label it A, B, C. And let's make it a little bit bigger so we can actually see what's going on with the triangle. So this is triangle A, B, C. They said that it was an angle of 30 degrees. So this is 30. And this is 90, so it's a 30, 60, 90 triangle, which is going to come in handy in a minute. if I look at the bottom from A to B, that's going along the y-axis. So that's just whatever y value we're at. And then the height is the tricky part. Let's see. 30, 60, 90 triangle. The small side, if this is x, then that means that this is x rad 3. So if I want to go backwards and I want to go from x rad 3 to x, I should just divide this thing by 3. So let's do that. Y divided by rad 3 must be this height of this triangle. So I think I can write out the volume, the area now, and then get the volume. The area is just the area of the triangle, which is half of y times 1 over rad 3 times y. I want it as a function of x, so that's half of the y value, which we said is square root of 16 minus x squared, times 1 over rad 3 times square root of 16 minus x squared. And that simplifies out to 16 minus x squared over 2 rad 3. So that means our volume is the integral from minus 4 to 4 of a of x dx, which will be the integral from minus 4 to 4 of 16 minus x squared over 2 rad 3 dx, which is 1 over rad 3 times the integral from 0 to 4 of 16 minus x squared dx, which is 1 over rad 3 times 16x minus x cubed over 3 from 0 to 4. And that is just 128 over 3 rad 3. So you can see that the most important thing for every single one of these problems is to draw your figure, draw the little thing with the area that you're adding up over and over. And then once you figure out that area, the entire integral falls into place.